electrostatics, electrodynamics, all of that stuff. So today, we start out with magnets, and then we put them all together and we have this glorious electromagnetism because it's super important in the X-ray tube and the whole circuit. It's sort of how everything gets fed with power. So we have to know how it works. So we'll do magnetism first. So we know that any charged particle in motion, whether it's flowing or spinning, creates a magnetic field. We know this because I touched on it like really lightly, so now we get nitty gritty, okay? So whether it's an electron in motion, like flowing down a conductor, or it can just be sitting and spinning like the Earth, right? We are rotating right now, and electrons do the same. They can flow down a conductor, but at the same time, they're also spinning. So that motion, whichever it may be, creates a magnetic field. So when it is flowing, the magnetic field created, and this is where it gets wordy and weird, but just look at the pictures too. It's perpendicular to the motion of the electric field. So whatever direction it's moving, so the top picture, that electron is flowing in the direction of the yellow arrow at the bottom, right? And it's got the cool speed lines behind it, like in a cartoon. So it's flowing, it's moving. Those rings going around it, those rings are perpendicular to the speed lines, right? Those rings are the magnetic field. So it's perpendicular to the direction that it's moving. Okay? Cool? Neat. The bottom one is the spinning variety. Oh, I forgot to tell you what it's called. So if it's flowing, it's called an orbital magnetic moment. If it's spinning, the magnetic field created is still perpendicular to the motion of the spinning. So we see that this one is spinning this way, right? You can see the direction that the arrows are going. And then these concentric circles are the magnetic field direction. So they are perpendicular to each other. When it's spinning, it's just called a spin magnetic moment.
What's the arrow on that bottom one? Is
This
that the
one?
way? So it's spinning and moving that
Well,
direction?
it could be. Like this picture has kind of multiple purposes. But for
Okay.
right now, just pay attention to this because the whole moving one I liked in this picture better.
Okay.
All right. So by nature, magnetic field lines are kind of random, but they do always have a north and south pole. So that's what all these little arrows are. Those are little areas that have magnetic field. Maybe they're electrons, maybe they're protons, whatever it may be, because anything that's charged, right, it doesn't necessarily have to be only electrons. That's mostly what we talk about, but just remember that it's protons too, because they're charged. So each one of those is kind of a little magnet. And the word we use for that is a magnetic dipole or a magnetic domain. All right, you'll hear both of them. And so this is when we're kind of random. You see there's this group that's kind of all going the same way, this group kind of going the same way. Okay? So by nature, we're a little random like that. That's how we are. And then we can become magnetized. So if we stuck that block, next to a very strong magnet, it would make all of those arrows align and look like the block down here on B. So once all of these align, now we basically just have a magnet. So now we have a north and south pole for the whole thing instead of a whole bunch of little different north and south poles that are all going different directions. So that's how we can magnetize certain materials. We align those dipoles or domains, make them all go the same direction, and now we have a magnet with north and south poles. So this whole concept is how MRI imaging actually works, which we don't really get into that. This ain't MR school. But it's based on that principle. We are aligning protons and then unaligning them repeatedly, and that's how the images are formed. Way more complicated than that, but that's the basic one. And so I kind of already said everything on here. This is how things become magnetized. Look, I got ahead of myself. But I do like this picture. That other one was from a different book. In this one, this is showing non-magnetized. It's just a different way of looking at it. It's still an electron. You can see the direction it's spinning, and you can see the magnetic field by the arrows. All those arrows are going in different directions, so we know that one's non-magnetized, right? So if this label was gone, and you're comparing the two, you'd be like, okay, well, these are all wonky still. They have not been placed near a very strong magnet. This has been not magnetized yet. This one though, all of our electrons are going the same way, they're all rotating the same way, and the magnetic fields are all directed in the same way. The north and south poles are all aligned, and now, whatever this little cylinder is magnetized. All right? And so once that happens, we get these bigger lines, right? So these are the magnetic field lines for the whole thing, instead of it just being a little arrow showing us. Now that whole thing is magnetized, we have a much bigger area of magnetic field. Okay? I know, this is rough, but it's worth it. So those lines that I was just talking about are called, they have 3 names. It's very annoying. Lines of force, lines of flux, or just straight up magnetic field. You'll hear me say magnetic field lines, magnetic flux lines. It's all the same thing. Those are the force fields created when magnetic dipoles align to create a magnet. So once on that last slide, once all of those little domains and dipoles lined up, now we have a much bigger magnetic field. So that's why those lines come out more significantly. So like on the top picture, you've got this bar, and you've got these lines coming out, okay? If it's on the outside of the magnet, those lines of force always flow from north to south. So that's why there are arrows up there. They're flowing from the north pole of it, and they're coming back down to make that elephant ear shape. So they go from north to south on the outside of the magnet. Now if it's the inside of the magnet, they're going from south to north. And we talk about the inside of the magnet in a minute when we get into how it works in the X-ray circuit. Okay? So the cartoon is kind of what it looks like if you add iron fillings, like little shaved tiny balls, pieces of iron, and just plop them down by magnets. You can actually see the lines. You can see how it's concentrated here, it's concentrated at the ends, just like it was there. All right? And there's another picture, I don't know, coming up, some University of Indiana, something, did their, yeah, it's on the next slide. Indiana University is on something. Indiana University Northwest, yeah, they did their own. But now it's kind of cool, you can see the flux lines and how the iron fillings are concentrated in certain areas. So there's a few different things that we can measure. So the stronger the magnetic field, the greater the number of flux lines, okay? If we have a certain substance that is easily magnetized and it's a very strong magnet, it's gonna have more of those lines, right? If we have more of those lines, we call that having a greater flux density. So density makes you think of how maybe thick or big something is. So if there are more of those lines, then we would have a greater density, right? Flux density, all we need to really know is that it's measured in Weber. We don't deal with flux density, we just need to know what it's measured in and what it actually is, okay? Are you cool with that? Because the book got real crazy about Weber, and I was like, we don't need to know that. Enough crazy stuff. We do talk about magnetic field strength, though. So the flux density was specific to how many flux lines there were, right? Which does relate to the strength of a magnetic field. But if we're just talking about measuring magnetic field strength, we're going to use Gauss and Tesla. Gauss is a bit older. So that's what we kind of first measured magnetic fields in? Yeah.
When you say like the flux lines, are you talking about the literal like lines that
Yeah.
you see?
So those, the elephant ear things, and then the ones on the top, which, I mean, is what the iron ore fillings down at the bottom are showing you, because we can't see those lines with our eyes, but when we add the fillings, then it shows us exactly how they're going. So yeah. Uh-huh. So Gauss was the original one. We've kind of advanced a whole lot, and we can make ridiculously strong magnets now. So Tesla is kind of the more recent term, and we needed that because we have like 10,000, like thousands and thousands, hundreds of thousands of Gauss now. So 1 Tesla is 10,000 Gauss. It just kind of made calculations a little bit easier. And Tesla is what you'll hear when you start being more around a radiology department, because that's what the scanners are measured in MRI. So you'll hear somebody say, oh, we have a 1.5 T or a 2 T or a 3 T. That's Tesla. That's how strong the magnet is within that scanner. Okay? Is that cool? We need to know the different types of magnets. So there are natural, artificial permanent, and electromagnets. So natural ones, there's this material called lodestone. It talks all about it in the book. I'm not gonna get into it, you can read that. The Earth obviously has a magnetic field. That's a natural magnet. North and south poles, all that good stuff. It rotates on an axis, right? It's a rotating thing, so it's creating magnetic field. It's fabulous. Artificial magnets, or artificial permanent magnets, those can be like the bar-shaped U magnets, the ones we saw in those pictures, the red and blue ones over there. Those were created. They're usually made of iron. It's easily magnetized, and it holds on to the magnetic charge very well. So that's what that is. You can demagnetize iron too, which we'll talk about. You can heat it up really, really hot, and it will kind of break that magnetic field. I thought it was interesting in the book. It was talking about old blacksmiths. Prior to the 20th century, experienced blacksmiths were easy to spot because the tongs they used to handle the heated metals had become magnetized after many years of standing in the same position in orientation to the Earth's magnetic lines of force. Heating the tongs in the forge and then pounding hot metal into shape on the anvil, the tongs had become well magnetized. So you could tell if they were good quality blacksmiths if his tongs were magnetized. I thought that was nerdy and interesting. So it's on page 55, 56 if you want. But it's real. Okay. So electromagnets, that's where it's at for us. That's where we want to focus our energy. I mean, please remember lodestone and earth are natural magnets, but electromagnets are what we're going to be talking about a whole lot. So you can make a very simple electromagnet just by coiling up a piece of wire. You don't even need to have anything in the middle of it over here. So if you coil up this wire and you supply a current to it, we're going to have moving what? If we have a current flowing, what's moving?
Electrons.
Bless your little hearts. Moving electrons. So then what's going to happen? Because we have moving charged particles. It's a magnetic field. So that's why we get the elephant ear lines, right? And so the direction of the current going kind of makes a difference. It's still going to go, this way because it goes from north to south. But that's the flowing, right? Depending on the current that it is, how big the wire is, we can make a really strong magnetic field. There's lots of variables that go in it. So all you really need is a wire and a battery, and you can make this happen. You can make it stronger yet by adding some type of iron core in the middle. Iron's easily magnetized, right? It's right there with it. But you see how adding that, we have more lines. So we have created an even stronger magnet yet. So there are more lines, that means we have a higher magnetic field strength, okay? So we had the coil, that was fine and dandy. We had an electromagnet, but we wanted it to be stronger, so we plunked the iron bar right in the middle. Then we supply the current, now we have a stronger magnetic field. They do get more complicated, and by golly, we talk about that today, but that's like as simple as you can get for an electromagnet, okay? Any questions about that? It is. So, we have some laws for magnets. There's only 3. They're pretty easy. We know all about repulsion and attraction. We knew about that before because we were kids and played with magnets. When we talked about it with, when we talked about that with intensity and energy and stuff, distance. So, oh, that was the inverse square. Anyway, yeah. We still have the inverse square law because the same thing applies. If you increase the distance between magnets, it's going to decrease their intensity between the two, the magnetic field, okay? And then magnetic poles. They all have a north and south pole. If you have a large magnet, if you chuck it to the ground and it breaks in half, what happens? You have 2 magnets. Each one has a north and south pole now, and you can just keep doing that, and then you have a whole bajillion magnets. But every time that happens, they're both going to have a north and south pole, all right? You don't just have your north in this hand and your south in this hand. Cool with those?
It's bringing up a lot of nostalgia of learning in elementary school. A simpler time.
Right. Okay, these 4 terms are important. Put a star by these, highlight them, whatever you gotta do. We gotta know definition of them and an example of them. So, all materials can be classified as one of these 4. Ferromagnetic. Who's heard that word before? Ferromagnetic? Okay. This is some type of material that is strongly attracted by magnetic fields. These materials are easily magnetized. What's one that I've said like 20 times already today? I mean, it's right there. Iron. Yes. So that's why it's good for a magnet, for an electromagnet. It's easily magnetized. It's very strongly attracted to by magnetic fields. Cobalt, also in nickel. Those are good examples, all right? Iron's the one we always remember, but if you have trivia night or something, you're like, cobalt and nickel too. I need to get out more. Paramagnetic, that's the next one. So these are slightly attracted to magnets. They are very loosely influenced by external magnetic fields, meaning they don't hang on to it very well. It's not a great relationship. Examples of paramagnetic materials are platinum and aluminum. Now, diamagnetic. These are things that are actually weakly repelled by magnetic fields. These things cannot be artificially magnetized. So we have water, we have lead, beryllium, and bismuth are just some examples, okay? Water is kind of the main one people tend to remember.
So, you said those cannot be artificially magnetized, so are there certain ones of these that, like, I don't like the paramagnetic, like, it says slightly attracted to magnets, but, like, can it be more magnetized?
Then it would be ferromagnetic. Because those are the ones that are easily magnetized and strongly attracted by magnetic fields. The big difference between these is diamagnetic is weakly repelled by magnets. And then when you come down to non-magnetic, it's just completely unaffected when you bring it into a magnetic field. So these sound similar, but that one is weakly repelled. This one's just kind of like whatever. So that's wood, glass, rubber, plastic, most things in life.
And those
Don't really care
can't be
about magnets.
magnetized at all.
Correct. Cool? I know it's wordy and gross, but they're simple definitions, and that's all we really got to know about it. Okay, 2 other new words. Permeability and retentivity. Permeability is the ease in which a material can be magnetized. So, what's an example of something that I've mentioned 20 times already that would be very permeable? Iron, thank you. It also is pretty retentive, right? The ability of a material to remain magnetized. They tend to hang on to their magnetic field once they become magnetized. So that's what those two terms mean. Doesn't really get any deeper than that. Just know the definitions. Alrighty then. Okay, lovely. Okay. So now we get to talk about how we can magnetize things. This is called magnetic induction. So these imaginary magnetic field lines are also called magnetic lines of induction. Now this is wordy, but just try to break it down. Not dancing, please. The density of the lines, so density of the lines, how many of them there are, right? So how many there are, is proportional to the intensity of the magnetic field. We've kind of already said that already. That's just the gross science way of saying it, all right? So the density of the lines is proportional to the intensity of the magnetic field. So if we have more lines, we have a stronger magnetic field. Right? Okay. So in that instance, if we place a ferromagnetic object near an intense magnetic field, it will alter the lines of induction due to that attraction, making the object temporarily magnetic. So we have this magnet up here, north and south, great. We just got a chunk of iron. If we bring it close enough, those magnetic field lines are gonna say, oh, we like iron, it's easily influenceable, so then it goes up there. Now, that iron bar is also a magnet because it's close enough to that very strong magnet. Those magnetic field lines are inducing that magnetic field in the iron now, okay? But it had to be something ferromagnetic, right? As soon as we move the iron farther away from it, it's no longer a magnet. We would need a much stronger magnet to permanently induce the magnetic field into it, okay? But we could do this with anything. So, if you take copper, which is not ferromagnetic, and then it just like sits by the magnet, nothing happens, okay? So it would have to be something ferromagnetic for those magnetic field lines to actually induce the field in something else. So that's why it doesn't work on copper, but it would on iron. And then if you move the iron, no longer a magnet. Okay? Okay, so that's the end of just magnets. Now we're going to take electricity and magnets. They're going to get married and it's going to be great. Our old friend Hans helped us figure this out. So, back in the 1820s, Mr. Oersted discovered the first link between electricity and magnetism, and it was by accident. I can't remember if he was a teacher, I think it was his classroom or his lab, I can't remember. But he had a very simple circuit. He had a battery, and a switch, and a wire, but his compass was sitting on his desk. So when he closed that circuit, so this is the sign in a circuit for a switch. It's open, so there's nothing flowing, right? When you close the switch, now the current's flowing, his compass moved. And he was like, well, what in tarnation? And then he was like, okay, so he opened the switch again and it moved back to where it originally was. And he was like, gosh. So then he kept doing it. Anyway, fashioned a simple circuit. Nearby compass would indicate the magnetic field when the circuit was closed. This is on, I think I left the old page number on from the old book. I did. Ignore page 76. God, I thought I got all those off there. 57. Ah, yeah, 57. So that was showing the direct link between electrical and magnetic fields. That's great. Charges at rest on a wire, not moving, no magnetic field, right? The compass does its thing with the Earth's magnetic field and everyone's happy. As soon as those electrons started flowing, then the wire produced moving electrons and therefore the magnetic field. Okay? You might be thinking, I wonder if it works the other way. And it does. But we'll talk about that in a couple slides. So, don't get too excited. I know you are. So, now that we're talking wires, and we know about magnetic flux lines and things, and I've said the word concentric a couple times, just kind of as a teaser. So, when we have a wire, so the picture at the top, the magnetic field lines produce concentric circles around it. So it's the flux lines, but it's weirder to picture it with a wire than it was with just the simple bar magnet, right? So if you have a wire flowing, the current's going up that wire, now you can see the magnetic field lines going out from it. It's perpendicular, just like we already talked about, right? So I'm just trying to get your head to like flip it into, now we're talking about electricity and wires and such, okay? So, if the wire is curved or looped, the magnetic field lines overlap inside the loop. So then when they come together, the magnetic field is stronger, right? Because there's more flux density right here. Oh, we're using the words we just learned. So there's more lines here because they're overlapping now that we have bent the wire, okay? So our magnetic field is a little stronger in the middle than it was out here. Make sense? Because it just keeps getting better. Now, if we take loops and stack them on top of each other, what does that look like? We just talked about an electromagnet, right? So the fancy word for it is a solenoid. If we stack the loops on top of each other, we create a solenoid. The magnetic field becomes even stronger within that coiled wire because we have all those coils stacked up against each other. And there's current flowing through all of those. We've got magnetic field going on. Everything's close together, so it's a lot stronger. All those lines are right next to each other, and then they come out, and that's when they spread out. You get the elephant ear effect, okay? And then, just like before, if we add a ferromagnetic material within that, it becomes even stronger. That was when we could plunk that iron bar right in the middle and have an even stronger magnetic field, okay? So that's how that actually works, a little more deeply, and you gotta know the word solenoid now. Any questions about that? I feel like I'm talking wicked fast, I'm sorry, but everyone's like doing the nod, like everyone's kosher with it. So if you're not, please let me know and I can say whatever I need to give or a different way. Okay? You're just good at lying faces now, and you're like, I'm just gonna look chill so she shuts up.
Just trying to take it all in.
Yeah.
I get it. I get it.
Just take it.
Well, that's why the disclaimer at the beginning, because if you read the chapter 4 class, you were like,
Yeah.
stick a needle in my eye.
Yeah.
Yeah. Okay.
Yeah.
So much talking. The strength of electromagnets and solenoids is determined by 3 things. The number of loops, which makes sense. More loops, stronger magnetic field, that makes sense. The strength of the supplied current. If we are supplying a dinky little current, what's our magnetic field going to be like?
Dinky.
Dinky. The permeability of the core. If we put iron in there, it's pretty permeable, right? We will increase our magnetic field strength. If we put this plastic handle in there, not much is going to be happening, right? Now, you're like, well, doesn't this kind of mean the same thing? And it kind of does. So, the effectiveness of a solenoid. Well, if a solenoid is effective, it's going to be creating a pretty strong magnetic field, right? So they are very related, but the book had them separated, so I wanted to keep them separated. So the effectiveness of a solenoid, that's the wire, right? The diameter of the coil makes sense. If we have a thick wire to supply the current to, we can have more of a current flowing, right? There are more electrons available that are making up that wire. If we have a really long wire that has a whole bunch of coils, that makes sense. Longer coil, more electrons, more flowage. And then again, with the supplied current. If we have a big fat wire, but we hit it with a tiny little current, not super helpful. So we would have to get it with a big current to make those electrons flow.
Sarah, can you say the thicker wire or so?
If it's thicker, there's going to be a lot more atoms, which means more electrons, right? Okie dokie. You're up. All right. Should have brought my clicker. Okay, now is when you can be excited if you're like, I wonder if we can go the other way. With a moving magnetic field creates an electric current. And it does. Michael Faraday discovered that. And it was only like a year after Oersted did his accidental finding. Michael Faraday was like, well, by gosh, I wonder. So he took magnets, started moving it close to a conducting wire, and saw that, yeah, when I move these magnets, it does induce a current to flow within this conductor. Magic, right? Science is so fun. So, he had to have a meter. This just says meter, but it's an ammeter. Why do you think it's called an ammeter? Sure, yeah. Current, amps, yeah. No, I'm so happy. That's just like made my day. So, yes, you have to have an ammeter. That's measuring amps, right? Connected to the conducting wire to measure the current. So when it's at 0, we have no flowage. When he started moving the magnets, it created a flow. He could see it on the ammeter, okay? Now, there's a big long story about all the Faraday's laws on page 60. And I would like you to read that section, okay? It's on page 60, starts out with electromagnetic induction, and it talks about all of Faraday's laws. I don't want to spend a whole lot of time on that because I wanted to make sure that we got to the other thing. So I know I told you to ignore the book kind of, but go to page 60, just read that little snippet there later. Because I want to make sure we can talk about this stuff. All right. So electromagnetic induction. That's what we're still on. We're still talking about solenoids. But there are two kinds of electromagnetic induction. We have a mutual, and then we have self-induction. Both of these are in the X-ray tube. Do we need to take a potty break? I feel like lots of people are going.
Sorry.
All right, no, I don't care. We'll take 5. I don't care. I forget to take breaks in class all the time. So you guys gotta remind me. Because that gets deep anyway, so.
Sarah, I'm sorry if I'm distracting, but like your silliness combined with the nerdiness is like my brand of humor, and I can't even with you. Like,
What's funny about the syllabus?
Oh dear. No.
So we don't need to know which law, because when I was reading the book, it said that there's 2 laws. They're just this law.
Just kind of read this section and you'll be fine. We're not gonna get too much into it.
Also, my younger niece, her name is Trinity, and when you said Electrinity, I so just got a new nickname for my niece. But I'm easily entertained, and the way you lecture is so entertaining to me.
I mean, it's pretty boring stuff. So I gotta try to.
I
mix it up a
think
little
it's
bit.
interesting, but I'm also a nerd, so big science nerd. So. But yeah, sorry, you're cracking me up, dude.
So, I originally
Electromagnet, they get married, it's great, like, just a little thing like that, like, I
Makes it
can't.
slightly more interesting. I'll say
Hey,
that.
you know what, being able to, you know, teach something in a way that like keeps your students interested is a good, you know, skill to have, you know?
I'll try.
Especially.
It's for a living, but it was nice to worth it. Like,
So you can make a solenoid out of copper and copper wire and an electric charge, and then you get a steel washer and you drop it in the tube and you can watch it flow back and forth.
Oh, yeah.
Change the voltage of how much current it's getting, and you can get it to sit right in the middle of the tube. It's pretty cool.
It just makes me happy when I saw like the little like iron shavings with the magnets. Like I still remember like how fascinating that was to me in elementary school when we did those, like learning about like magnets and North and South Pole and trying to put the magnets, the North and North together, and they're like,
Oh, yeah.
like and we're all like,
Calling each other.
I can do it, like,
I can make them
I will
touch.
make the touch. No.
They will stick together. I will make it happen.
Like you get them, like you get them, like almost, and then they like go like that, like.
Yeah, and then you jam the magnet.
But yeah, the little iron shavings, those things I remember is like watching them move, like with the magnets, like when you drop the magnet in them, you're like, oh my gosh, that was amazing.
Little draw pads with the metal shavings.
Yeah, yeah.
Clown faces and stuff.
Yeah, like you could draw like the beard and the mustache. There was ones
The
that.
bald guys.
Yeah, yeah.
Give them eyebrows. Crazy
Yes,
mustaches.
yes, I do. I think we had a few of those. Because they were totally crafted made, you know.
Oh yeah,
But they still work.
It was a little plastic
Barely like a little plastic.
sheet over cardboard with a magnetic pen and iron shavings.
Yeah, yeah. Man, was it entertaining.
I've been going for hours usually.
Right? You're like,
Car rides were non-existent because I
give
had
a
something
blow
to
home
do.
today, like.
Although I will say, Mr. Sketch is essentially working the same project.
I'm not ready for this.
Well, yeah, because like when you move the thing, it's moving the something, the thingy inside of it. That's still like those people that are like crazy talented with Etch a Sketch, like they do like the Mona Lisa and stuff. You're like,
I've tried to make a drawing.
It's like, I just
you know, like, I still remember how proud of myself I was when I got like a perfect diagonal line from one corner to the other. I was like,
Like the perfect star, perfect circle.
I was never that
I
good.
tried for hours. I managed to get like one perfect circle.
It's so funny though, because like my stepdad got a bunch of like old school toys for my nieces for Christmases last year, and the Etch a Sketch was one of them. And they love that thing, dude. Like it's a timeless toy.
When you can sit there and draw and you use your hands and
Yeah, yeah.
like artistic skill necessarily with pen and paper and pencil.
Dude, I'm gonna be like,
And you can erase it.
Okay, we got 30 minutes and like 16 slides, so we'll see how that goes. Okay. Mutual and self-induction. So with mutual induction, we have two coils and we put them close to each other. We have a current supplied to the first one, this one. So that current starts flowing through that solenoid, right? And then we have magnetic field business going on. And if this is close enough, just like before, if we put something non-magnetic or at least ferromagnetic close to something that has a strong magnetic field, we have a magnetic field over here. And because it's moving, because that current is flowing through the first wire, we have a expanding and contracting magnetic field because it's alternating current that's being supplied to that. Ooh, it tossed in something new. So if we have alternating current supplied to this, that's going to make our magnetic field be moving, essentially. So that's why the magnetic field over here induces this current to flow over here. We don't have to like shake that first solenoid around to make the magnetic field move. The current makes it happen. So the current supplied to the primary coil, or the first one, we're going to get into primary and secondary. That all is in the X-ray circuit. So that first one that we supplied the current to is called your primary circuit, because technically it is a whole circuit. That induces the current in the secondary coil, or secondary circuit.
So
Okay.
is that kind of like how, like with induction, like you don't have to touch the thing for the.
Yep,
Okay.
that's why it's electromagnetic induction, because you don't have to have contact. So then self-induction, we have a single wire that induces current in itself due to an alternating current. So we could have just this one wire sitting there that has this alternating current in it. You don't have to have the second wire, okay? And so we get into kind of both of those. But that's the basic definition. So, those, yes.
When you say induce
switching and current, does that just mean like starting?
Yep, it makes it happen, yep. Like when you get induced when you have baby, it's just you make it come out. It's boring.
So for the self one, like, get rid of that secondary circuit over there.
Yes.
So you got your primary circuit, so is it like how those magnetic lines are like that? Is it just doing that inside
Mm-hmm.
the primary?
Yep,
Like just the one?
yep.
Or outside of it?
The dash lines, she's talking about the dash lines.
The dash lines.
Is it happening, if you cut away the secondary?
Yeah, if it's just
Yeah,
like
it's still got a magnetic field,
around the outside and the inside, or?
Well, yeah. but it wouldn't be going in anything else, it would just be there, and then you could put something next to it, and it would induce current to flow. So, but you don't have to necessarily have the two wires, that's why it's just self-induction, and there's only one, and then there's two. And you'll understand more at the end of this chapter, because there is mutual and self-induction in the X-ray tube. There's two different kinds of transformers that function in the tube, and they both use one of those. All right, so this seems like switching gears, but it's all related because we gotta talk generators and motors. Because they all work on the same. I see. Thank you. So, an electric generator is something that converts mechanical energy of motion to electrical energy, okay? So I like, your book has pictures, but this one was very simple and I just liked it. We've got a crank, we've got the hand that's gonna move the crank, it's gonna move the thing, and then we're gonna induce a current, okay? That's about as cool as it gets. So we have mechanical energy, that's the dude or the girl, whoever is gonna turn the crank. We are creating motion of the magnet, so there's north and south poles on that bar, right? He's gonna turn the crank, it's gonna make the magnet move. When we have a moving magnet, it's gonna induce current to flow in this wire, okay? So that's like the most basic generator you can have. Now, depending on what type of current flowage, we have AC generators and DC generators. So this is the we're not gonna talk a whole lot about the top of that picture. I'm more interested in the wave. So, an AC generator is gonna use slip rings or brushes. And if you wanna Google what they look like, that's fine, but I don't really care if you know what they look like. I just want you to know what they do. So what this allows is constant contact between the things that are spinning and the current, okay? So it allows the circuit materials to be stationary, but the armature, that's the thing that the dude was turning, okay? They are still in contact even if it's turning. Because if you imagine all these wires together, if you turn something, you have to unwind it. But this is so you don't have to unwind it, because there are wires that are allowing this current to flow. And so these slip rings and brushes allow this constant contact. They're able to just kind of be together and rub on each other. Sounds fun, isn't it? But it allows that to constantly rotate, and still the current is able to move. But the rest of it, the circuitry part, doesn't have to move. Does that make sense? Yes. So, if you have this circuit, and you have this big crank over here, and you have to turn this crank, you still need this wire connection to allow the current to flow. So you have to have these slip rings or brushes, and they just allow that contact. They rotate against each other. So as he's turning, or she is turning that, there's still contact without jumbling up all these wires that are connected, okay? It allows the electrons to flow without interruption. So, yeah,
So where would this be used in?
well, it's all in the X-ray tube. We're getting
Okay.
there. This is we gotta go from the ground up.
Okay.
So, there's a big generator in the X-ray machine.
Okay.
Well, this is like any generator. I mean, the kind you need when your power goes out. So, We want electrons to flow without interruption, and that's great. But by using these slip rings and brushes, we end up with a waveform that looks like this. Familiar? No?
Wave.
Yeah, it's a sine wave. It's the same with electromagnetic energy. We had an up and a down, so that should look super familiar. That's why we talk about all that in chapter 3, or 2, whatever chapter it is. Okay? Because it's all coming back to haunt you again, and it gets worse. But that's the wave we get with AC. So that's alternating current, right? It goes up and it goes down. That's the change in directions. Does that make sense and come together for you a little bit? Okay, because on the next slide we talk about DC generators, which is direct current. You're like, I hate you, Sarah. So, this whole wave, so from 0 to 360, picture the person. That's one revolution. So if they start with the handle at the bottom, they go all the way around, that is one cycle. Okay? So it's going to go up, then it's go down below 0, and it's going to come back up and stop right there. That's one revolution of this. Okay? One cycle. What else makes you think? What else do you hear in your head when I say cycle? Yeah, or hertz, a cycle per second. So now we're getting into the whole frequency thing. So one revolution of that arm for this generator is one cycle of this wave. So, now you're really gonna wanna punch me.
You're about to give us now, right?
Nope, not yet. I'm just gonna keep talking.
Sorry.
So, this here says it's voltage, right? So voltage is going up in this direction, going up in this direction. So we don't really want the voltage to like go down, and we don't really want it to fluctuate, ideally. Does this fluctuate?
Yeah.
Yeah, it's ridiculous. You go all the way up, then all the way comes down, hits 0 3 times. That's not great. It makes it really hard to measure the voltage that's going to be flowing in this circuit. And if we're going to be producing x-rays and blasting people with it, we want to know exactly what voltage we're going to have. So it's not great for us to have this alternating current. That's why we prefer direct current. We like DC. But those electromagnetic induction things require the alternating current, right? Because we need those electrons to be changing directions, because that's what induces the magnetic field, right? So it gets tricky. So with this, with the DC generator, this is using a commutator ring instead of slip rings. This allows the current to flow without interruption, just like slip rings and brushes. But now it routes the current differently. And it seems really confusing, but that's why I'm like, just avoid the book, because this is what you need to know. You don't need to know how it routes it differently, just know that it does, okay? So this commutator ring has the same purpose as the slip ring or the brushes in the AC generator, but it's gonna reroute the current differently. So it has taken that second part of the cycle and flipped it up. So, do we have a little less fluctuation in our voltage now? Yes, and that's what we want. It's still fluctuating, because it's still going up, and then it's going down to 0, it's going up, and then it's going down to 0, but it's better. That's better, okay? Does that make any sense? Yes? Just nod, okay, thanks. So, but now, the electrons are flowing in the same direction. Now it's direct current. That's why it's a DC generator. So it has totally changed the current, and that's fine. That's what we needed. And we have another thing in our circuit that changes this too. We'll talk about that in a minute. But that's the two generators you need to know about. We got AC, we got DC. You know that one uses slip rings or brushes, one uses the ring. They have the same function. The DC, though, alters the current so that our electrons are now all going in the same direction, We have less fluctuation in our voltage for that circuit. Alrighty? Okay. Onward. Now, on the other end of that is a motor. Now, we're going the other way. We're converting electrical energy to mechanical energy. As current flows through the coil, a magnetic field is created. The lines of force are attracted in one direction, but then they're also repelled in another direction. Because this current is flowing so fast, the magnet doesn't know what to do. It's attracted one time, but then it's repelled another time. So the magnet just spins. It's constantly trying to catch up with itself. Like, oh my God, I want to be in line with this one, but this one, and I don't like this one. So then it just spins. And that's as simple as that gets. Okay? So we induce a current, and we make the current flow in the wire. The magnet in the middle is like, oh God. We have all this fluctuating magnetic field business. So the magnet just spins to try to catch up.
So how it has those arrows, so is it just getting mad at some electrons and just like throwing them out? Like,
So we have moving current. So the wire is going to have a magnetic field around it, but it's going to be moving, right? So then the magnet that's in the middle with the north and south poles is going to want to try to align itself with it, right? Because opposites attract. So the current is going to be moving so fast, that magnetic field is then going to be moving, and that magnet in the middle is going to try to catch up. So then it just keeps spinning.
so that's the direction of the current. It goes 1, 2, 3, and then 4?
Yeah.
Okay.
I mean, I'm not going to be quizzing you about the arrows. I just need you to know, like, how it works.
Just trying to understand.
Gotcha. Some people get really focused on like an arrow, and I'm like, don't worry about the arrow. It's all good. But if it helps, then by God, do it. Okay. So, we have this alternating current induction motor. This is inside every X-ray tube. There is a rotor. It's a shaft made of copper, soft iron. It is attached to an axle. And there's some other pictures in your book too. And that's going to turn the device. So you've heard the word rotor, right? In the lab. This is how our anode gets the spinach. This is the whole point. We've done like 8 chapters just to get to this point. You're like, could have just said that. There's also a stator. These are the 2 main parts of this piece of equipment. The stator is a group of stationary coils of wire that go all the way around the rotor on the outside. So the rotor is in here, okay? These wires are the stator. These are things we're going to talk about in a minute. That's what it can look like in real life. They all look a little different depending on the manufacturer, but it's the same idea. This induction motor powers the rotating anode of the X-ray tube. And it's that whole concept of the magnetic field being created by this current, and then the magnets in the middle trying to catch up. So they just start spinning like crazy to catch up with that other moving magnetic field. So it's that same concept. That's why we get a moving current, or why the rotor starts to spin so bloody fast. Yes?
So, the stator makes the rotor move?
Uh-huh.
Okay.
So there is page 66 in your book. Shows you like if we chopped it, right? Like we chopped this in half right here so we could see the cross section of it. Those little things are magnets. So look on page 66, right next to the hand thing. You can see all these magnets. The rotor windings obey the motor principle, which is what we talked about, this motor. There was the current induced in those wires, so the coppery looking wires right there, we are inducing a current to flow in those. Everything's connected in the whole circuit. The current starts to flow through those stator windings. Now we have a magnetic field, right? All those little magnets in there start dinging, kind of. You can think of it as dinging. And then we have this iron rotor. Iron is ferromagnetic. It's very reacting to magnetic fields, right? So then it's like, ooh, this is a moving magnetic field. I want my south to line up with that north, but it keeps moving. So then it just keeps spinning. Okay? So that's what the picture in the book is trying to show you. It's got all these north and south poles. The stator windings have the current flowing through them. As soon as that current starts to flow, there's that magnetic field, and then the rotor is iron, and it's like, oh, opposites attract, but I can't find it, we can't stop, that's moving, so I'm just gonna move too. And then the second you cut off the current, and it's not flowing anymore, then your rotor stops spinning. Good, bad, ugly? I wanna go home. Yes.
So is it made of iron? Because that says copper. Or is it
Copper
both?
and soft iron.
Okay.
We talk
Oh,
about
yeah,
why it's made of a lot of different things
Okay.
later, because you'll have to know what everything's made of too, but we're not there yet. Okay? So is that okay? Do I need to say any of that again? You're like, just please don't finish lecture. I understand. Okay, we may not get through all of this today, and that's fine. What?
Nothing. Yeah, she said it, not me.
Transformers. We're not done yet, though. We still got 13 minutes. So, we've talked about this part, right? We know what this thing on the left is. That was our electromagnetic, solenoid, all that fun stuff. So, we need those to make transformers. The whole point of a transformer is to alter the voltage or amperage of an entire circuit. Or current, I guess. So if we took this iron bar and we just kind of stretched it out and connected the bottom, we could end up with something like this. Now once you connect the two ends, our magnetic field just sort of chills. It's still moving because the current is moving, but now our field lines are all kind of just hanging out in here, okay? They cannot escape, they remain concentrated. So, smart people, what do you think would happen if we put another wire over here?
It's gonna transfer the current.
So we're gonna have a moving magnetic field, have another wire, and it's gonna be like, oh yeah, I should probably flow, yeah. So then it's gonna induce current to flow in that other wire. That was that whole like mutual induction business, right? So the first wire that we're supplying the current to is the primary coil. We've mentioned that already. If another wire is added, the magnetic field induces a current to flow in that wire. That is the secondary coil. Now, something I already mentioned too, transformers only operate on AC. Why did I say that?
Because it needs the alternating current to make a current.
Yes. So, the electrons have to be changing directions, right? To make that magnetic field happen. Once the magnetic field happens, we induce another current, and that's great, but that doesn't work with DC. So transformers have to have an AC supply. Now, the useful part, or very important part, I guess, if the secondary coil has more turns or windings, right? You're gonna hear both of those. If it has more turns or windings than the primary coil, the voltage is increased proportionally. So, if this one has 5, and this one has 10, we have double the number of coils, and therefore we will double the voltage that's coming out of that secondary wire. Okay? Not terrible, right? But it's just voltage we're talking about. Now's the math. Oh, sorry. It's not that bad though. It's better than the inverse square laws. You don't have to square anything. You're just plugging numbers in. So there will be problems related to pictures like this. You have a transformer that has a primary and a secondary side. It's telling you the voltage and the amperage that is supplied. And what's this?
Power.
Yeah, power, watts, all that. So, we got that, and all you're doing is multiplying what to get powered?
P equals I
ID.
times V.
Right, amps and volts. And I hate that there's an A, this was just a Google picture, it should be an I, but that's okay, don't get confused. So, and then it tells you, all right, 20 turns over there, now I got 400 volts, 2.5 amps, still have 1,000 watts though. So we can tinker and change the voltage and the amperage with these transformers, but still end up with the same amount of power usage, okay? And that's important. I was gonna get ahead of myself, I'm not gonna do that.
Is
I'll work with
that
it.
like kind of like the mass reciprocity or whatever?
Kind of. It's more like energy conservation. Because we can't, energy and matter conservation, right? We can't destroy or create it. So we have the same amount of energy flowing, right? Because volt is energy. But we still have the same amount of power, but we can manipulate it to do the things we want. So you see that that's a step-up transformer and step-down transformer. Those are both transformers in the X-ray tube. Or in the X-ray circuit, I guess, not the tube. And so sometimes we want the voltage to be really high. Sometimes we want the amperage to be really high. Well, we have to give and take, right? We're gonna have the same amount of power because it's energy. We can't create or destroy. But if I need the amperage to be really high, what do I have to do to the voltage? Decrease it.
When I said mass, I meant MAS, reciprocity. You know what I mean? Like,
Yeah.
Okay.
I do. So, the step-up transformer is increasing the voltage. The name of the transformer is telling you what it's doing to the voltage only. But what I need you to remember is that when voltage goes up, amperage has to go down. Because I'm definitely going to ask you questions about which transformer increases amperage. And so read that question carefully because you're going to see increase and want to say step up real bad, but it's amperage. So if it's increasing amperage, the voltage is going down, so it would be a step down transformer that I'm asking you about.
Say that again, when voltage goes up.
Amperage has to go down because we have the same amount of power on both sides.
Did you, wait, you said amperage first time.
If amperage goes up, voltage goes down.
Yes.
And vice versa.
Yep.
You said step up increases voltage.
Yes, the transformers are named for what they're doing to the voltage only.
Okay.
So step up increases voltage, step down decreases voltage. But you'll get questions related to amperage, so you've got to know that they're the opposite.
I feel like you just said like two opposite things.
I don't think so. So, there is an example here, and I have examples on a fun little worksheet. I know you love those. But we're getting close, and we're not going to get through. We got 6 more slides. We talk more about transformers and then more electrical stuff, so we'll do that next week. But what I want to tell you is RadTech Bootcamp. No, you need it. It's very, very helpful for this next stuff. So I've got the assignments built. I'm going to post them. I don't know how Russ Ann and Nicole did it over the summer, but my instructions might be a little bit different. Same concept though. You got to watch the videos, take the little quizzes that go with each video, and then every now and then I have you take a big assessment at the end. So there's one this time where there's like 3 videos, and then I need you to do the big assessment, and it says that on there. And then there's another one where there's a whole bunch of little videos, but some of them are for a different chapter we haven't done yet. So I just want you to do a few of the little quizzes and show me that you did those, okay? It's still 85%. Nicole did the 85%? Okay. Something that I'm gonna do now though is when you take your screenshot to upload it, don't crop it, because I wanna see your initials in the top right of that picture. It shows on your phone, it shows on your computer, but we had cheater pumpkin eaters sharing pictures. And So don't do that. I wanna see your initials at the top.
So what do we look up in Rad Tech boot camp for these?
It's gonna be on campus. I built them, I just haven't put them up yet, because
Okay.
you guys would be like, what do I do? So that's why I waited till now.
Okay.
So it tells you, hey, it tells you exactly where to go, which course to look up, and which videos you're gonna watch, and when I need you to do the big assessment. You can do one big screenshot, you know, you can see all 3 quizzes and the assessment. One's fine. If you need to do multiples, I don't care. Just make sure that I can see your initials and you get 85%, and you'll get full credit. If you don't have at least 85% on it, then the scoring, you'll see how it's scored whenever the assignment's posted, and I'll do that right now.
Are you going to let us do multiple just in case? Is it unlimited like it is for?
Attempts, unlimited attempts.
Yeah,
Yeah,
okay.
We post, let's show them.
yeah, I'm gonna turn it on right now. I didn't wanna do it before, because everybody would have a heart attack. Before the test, so you've got a couple of weeks. Here, just, hold that thought.